Welcome to the Junos OS Fundamentals module, which introduces the Junos OS and describes its basic design architecture. The module also explains traffic processing for transit and exception traffic. Finally, the module provides a brief overview of Junos devices. The Junos OS provides a common language across Juniper's routing, switching, and security devices. The power of one Junos OS reduces complexity in high-performance networks to increase availability and deploy services faster, with lower total cost of ownership or TCO. At the end of this module, you will be able to describe the Junos OS and its basic design architecture, explain traffic processing for transit and exception traffic, provide a brief overview of Junos OS devices. The Junos OS functionality is compartmentalized into multiple software processes. Each process handles a portion of the device's functionality. Each process runs in its own protected memory space, ensuring that one process cannot directly interfere with another. When a single process fails, the entire system does not necessarily fail. This modularity also ensures that new features can be added with less likelihood of breaking current functionality. Junos OS is the trusted, secure network operating system powering the high-performance network infrastructure offered by Juniper Networks. It provides industry-leading performance and scalability and is built on open-source operating systems. Junos, depending on the device, runs on a modified and hardened version of either free BSD or Linux. All platforms running the Junos OS use the same source code base within their platform-specific images. This design ensures that core features work in a consistent manner across all platforms running the Junos OS. Because many features and services are configured and managed the same way, the setup tasks and ongoing maintenance and operation within your network are simplified. What sets the Junos OS apart from other network operating systems is the way it is built. It's a single operating system delivered in one software release track and with one modular architecture. Click each label to learn more about its features. Another aspect of Junos modularity is the separation of the control plane and the forwarding or data plane. The processes that control routing and switching protocols are clearly separated from the processes that forward frames, packets, or both through a device running the Junos OS. This design enables you to tune each process for maximum performance and reliability. The separation of the control and forwarding planes is one of the key reasons why the Junos OS can support many different platforms from a common code base. The example illustrates a basic view of the Junos architecture and highlights the control and forwarding planes. The routing engine, or RE, performs the control plane functions of a Juniper Networks networking device. The RE is the brain of the platform. It is responsible for performing protocol updates and system management. The RE runs various protocol and management software processes that reside inside a protected memory environment. The RE is based on an x86 or PowerPC architecture, depending on the specific platform running the Junos OS. The RE maintains the routing tables, bridging table, and primary forwarding table, and connects to the packet forwarding engine, or PFE, through an internal link. Note, although all Junos devices share this common design goal, the actual components that make up the control and forwarding planes vary between the different Junos devices. For additional details about a specific Junos device, refer to technical publications. The PFE, shown below the dashed line in the image, usually runs on a separate hardware and is responsible for forwarding transit traffic through the device. In many platforms running the Junos OS, the PFE uses Application-Specific Integrated Circuits, or ASICs, for increased performance. Because this architecture separates control operations, such as protocol updates and system management, from forwarding operations, platforms running the Junos OS can deliver superior performance and highly reliable deterministic operation. The PFE receives the forwarding table, or FT, from the RE by means of an internal link. FT updates are a high priority for the Junos OS kernel and are performed incrementally. Because the RE provides the intelligence side of the equation, the PFE can simply perform as it is instructed. That is, it forwards frames, packets, or both with a high degree of stability and deterministic performance. This architectural design also makes possible the incorporation of high availability features like graceful routing engine switchover, or GRES, non-stop active routing, or NSR, and unified in-service software upgrades, or ISSUs. As discussed earlier, the RE is the brain of the platform and is responsible for performing protocol updates and system management. Click each label to learn more about the RE and its functions. The PFE is the central processing component of the forwarding plane. The PFE systematically forwards traffic based on its local copy of the forwarding table. The PFE's forwarding table is a synchronized copy of the information created on and provided by the RE. Storing and using a local copy of the forwarding table enables the PFE to forward traffic more efficiently and eliminates the need to consult the RE each time a packet needs to be processed. Using this local copy of the forwarding table also enables platforms running the Junos OS to continue forwarding traffic during control plane instabilities. The PFE also maintains Layer 2 bridging information. In addition to forwarding traffic, the PFE also implements a number of advanced services. Some examples of advanced services implemented through the PFE include policers that provide rate limiting, stateless firewall filters, and class of service, or COS. Other services are available through special interface cards that you can add to the PFE complex. Transit traffic consists of all traffic that enters an ingress network port, is compared against the forwarding table entries, and is finally forwarded out an egress network port toward its destination. A forwarding table entry for a destination must exist for a device running the Junos OS to successfully forward transit traffic to that destination. Transit traffic passes through the forwarding plane only and is never sent to or processed by the control plane. By processing transit traffic through the forwarding plane only, platforms running the Junos OS can achieve predictably high performance rates. Transit traffic can be both unicast and multicast traffic. Unicast transit traffic enters one ingress port and is transmitted out exactly one egress port toward its destination. Multicast transit traffic also enters the transit device through a single ingress port. It can be replicated and sent out multiple egress ports, depending on the number of multicast receivers and the network environment. Unlike transit traffic, exception traffic does not pass through the local device. It requires some form of special handling. Click the Example button to view the examples of exception traffic. Junos OS sends all exception traffic destined for the RE over the internal link that connects the control and forwarding planes. Junos OS rate limits exception traffic traversing the internal link to protect the RE from denial of service or DOS attacks. During times of congestion, Junos OS gives preference to the local and control traffic destined for the RE. The built-in rate limiter is not configurable. Platforms running the Junos OS come in many shapes and sizes and are targeted for a number of deployment scenarios. The platforms running the Junos OS span switching, routing, and security, and are well suited for a variety of network environments. As the heart of all these platforms, the Junos OS provides a consistent end-to-end IP infrastructure in both small enterprise environments and the largest service provider networks alike. Let's take a closer look at each product family. These are some routing devices that run the Junos OS. PTX series, MX series, ACX series. Click each routing device label to learn more. The switching devices that run the Junos OS are EX series, QFX series. Note that for more information on all of Juniper's switching devices, refer to the displayed URL. Click each switching device label to learn more. The SRX series services gateways are the primary family of security devices that run the Junos OS and provide up to 2 terabits per second of full duplex throughput. The SRX series family is designed to meet the network and security requirements for consolidated data centers, managed services deployments, and aggregation of security services in both enterprise and service provider environments. For additional, in-depth details on the SRX series, refer to the displayed URL. For more information on all Juniper security devices, refer to the URL displayed on screen. Juniper Networks software-defined networking, or SDN products, do not all run the Junos OS. They are a group of products designed to integrate Junos into cloud-based solutions. For a full overview of Juniper's SDN products, refer to the displayed URL. These products include NFX Series, Contrail Cloud, North Star Controller, Wandle IP, or MPLS View. Click each SDN product label to learn more. The Junos OS can also run as a virtual machine or VM using either VMware or kernel-based virtual machine or KVM as the host software. Click each label to learn how the Junos OS can be run as a VM. The Virtual MX or VMX is a full-featured carrier-grade router that offers the same quality and features of the physical MX series platform. The VMX provides complete control, forwarding, and management planes. The software emulation of the MX hardware is executed down to the level of compiling the microcode of forwarding ASICs into x86 instructions. This ensures that VMX packet handling and forwarding is identical to that of a physical MX router. For additional in-depth details on the VMX series, refer to the displayed URL. As you have seen earlier, Junos started out as a single entity. In traditional Junos, the control plane, forwarding engine, and all hardware drivers are modularized components of a single image. This software image is tightly bound to its underlying hardware. Virtualized Junos takes advantage of virtualization technologies to run Junos in a virtual machine on top of the KVM or VMware hypervisor. Note that all components of the Junos OS are still fused into a single image. The VSRX and VMX products are examples of virtualized Junos. Further development of Junos took the advantage of virtualization further and separated the PFE software and platform-specific components from the core OS. The control plane and the daemons attached to the control plane remained with the FreeBSD kernel. But the operating system was opened up to external APIs, and the PFE and platform-specific software was no longer directly embedded in the OS. Disaggregated Junos separated the platform drivers and the forwarding engine, PFE software, and is running them in their own virtual environments directly on top of Linux. Click the Disaggregated Junos Advantages button to view the advantages of disaggregated Junos. The next stage of evolution of Junos follows the trend of cloud computing, where systems leverage pools of hardware to perform tasks. This is the core concept of Junos Evolved. With Junos Evolved, the legacy-free BSD kernel is removed. Because the core functions of legacy Junos were attached to the kernel directly as software daemons, the daemon processes have been redesigned to run independently of the kernel. In other words, they have been rebuilt as applications, independent from the underlying kernel, but based on the same functionality and code concepts of the original daemons. In legacy Junos, information related to a daemon is managed, modified, and stored by the respective daemon. When that daemon experienced a fault or restart, the information it manages and stores is lost, unless a system is implemented to run a backup of the daemon, which tries to synchronize its information with the master daemon. This type of hot standby is inefficient and difficult to manage. With Junos Evolved, the applications that perform functions no longer store the information they process internally to the application. The application is a consumer or publisher of information. Information is sent to the application. It processes the information according to its design and publishes the results to a centralized, distributed database, much like a data center environment. If an application experiences a fault or is restarted, the new instance of the application retrieves the state information that the previous instance of the application had stored into the database, and the information is not lost. Because the functions of Junos Evolved are application-based and run on a Linux hypervisor, third-party applications that are developed to run on the hypervisor can be implemented as well. And because the information related to all processes on the device are stored in a distributed state infrastructure or database, third-party applications can be developed as consumers of that state information, which retrieve information from the data store for administrators, management platforms, and so forth. They can also be developed and implemented as publishers of information, which can publish information into the data store as long as it is formatted properly and utilizes the built-in APIs. Junos Evolved is currently aimed for the data center or cloud use cases, and as such is able to run on commercial generic servers using merchant silicon or on supported Juniper hardware devices. Note that for more information on Junos Evolved, refer to the displayed URL. For more information on Junos software disaggregation, refer to the displayed URL. You have reached the end of this module. In this module, you learn to describe the Junos OS and its basic design architecture, explain traffic processing for transit and exception traffic, provide a brief overview of Junos OS devices,